Today we are here with another session on Canonical Ensemble. In this session, we'll be talking about the first part of the Canonical Ensemble, and this part is very important. Canonical Ensemble is the most important topic from thermal and statistical physics. So we have to do it, and this topic is very easy. You can easily attempt questions from this. So let's delve into it. So, everything is all right, I hope. Audio, video, there is no issue. Just confirm. Good morning, Ajay. Okay, so although good morning, Harry. Look, although there are 3 ensembles, in the most important topics there is only canonical ensemble. Now let me briefly tell you what is the basic difference between these 3 ensembles. We have micro canonical ensemble, and grand canonical ensemble. In micro canonical ensemble, there is no energy or particle transfer between the systems. Okay, so energy as well as particle E as well as particle number is denoted by N. E and N remains constant. Now if it come to canonical ensemble, in canonical ensemble, although particle exchange is not allowed, but energy exchange is allowed. So this is canonical ensemble. In grand canonical ensemble, both particle as well as energy exchange is allowed. So if I talk about the micro canonical, in micro canonical you can imagine that the boundary is rigid. Neither heat nor particle can be exchanged. So this is an isolated system. Microcanonical ensemble maybe deals with isolated system. Now there is something called closed system. It is applicable to isolated. This is micro canonical. Now when we talk about canonical, heat exchange is allowed, but as this is a closed wall, particle exchange is not allowed. Okay, this type of wall is called closed. Now there is something called open system. So it allows the heat flow as well as it also allows the particle exchange. This is done in grand canonical. So you understand the basic difference between these three, micro canonical, canonical and grand canonical. For the time being, we'll focus on this canonical part only. Good morning, Molly. So in canonical, energy can be exchanged in terms of heat, and particle remains constant. So just write a line before I start. In canonical ensemble, the energy E of the system becomes variable and can have values from 0 to infinity. To understand this canonical ensemble, we are considering a system, and let's say it is kept in the surrounding of a reservoir. This is the whole universe we are drawing. Inside the box we have the whole universe, let's say, and we have system. This is the system, and outside of it is reservoir. This is the system, and the outside of it is reservoir. So you know, system and reservoir, we have already talked about reservoir. Reservoir, you can say that it is an infinite pool of heat. If you take some heat from that and if you give some heat to it, the temperature of the reservoir does not change. So if you keep a system in contact of a reservoir, and if it has a temperature, let's say T, the system will also maintain the same temperature T. Okay. Now the system, we are denoting it by A, and the reservoir we are denoting it by A prime. The corresponding energy in the system will write at ER, and the energy value for the reservoir will write ER prime. Okay. So A is the system, A prime is the reservoir. So we consider the given system A, and you know, this all is a closed wall, so it will allow the exchange of energy between the system and reservoir, but it will not allow the exchange of particle. Now because of the exchange of energy, there will be several number of microstates. Okay, depending on the energy values, different states will be created. So we consider the given system A immersed in a very large heat reservoir. Let's say A prime. In the equilibrium, both the system and the surrounding heat reservoir would have the common temperature, let's say T, but their energies would be variable. And they could have at any time, let's say, T values anywhere between 0 and E0. Now what is E0? E0 is the total energy of the reservoir and the system. E0 is equals to energy of A. Energy of A, we are denoting it by ER, plus the energy of A prime, that is ER prime. I hope this is clear till now. So it is like if at any particular time the system is characterized by some energy ER, the reservoir would be having an energy ER prime, right? and this sum is a constant. This total energy will remain constant. Now, you see, this reservoir is much larger in size if you consider the size of the system. Now, since the reservoir is much larger than the given system, we can consider the energy of the reservoir must be much less than the total energy E0. Can you write it? If it is so, you see, ER plus ER prime is equals to E0. That means ER by E0 is equals to plus ER prime by E0 equals to 1. Therefore, ER by E0 equals to 1 minus ER prime by E0 is much less than 1. Same thing. Now, this line is very important. With the state of the system let us say denoted by ER, any state will be denoted by its energy value. Okay, depending on the energy value, the state is changing. The state of the system ER, the reservoir can be in any of the large number of states compatible with the energy ER prime. So, let the number of the such state is omega. Let the number of such states is denoted by omega prime, which is a function of ER prime. So, what it is actually saying, for a particular value of ER, this reservoir can be having the value ER prime. So, there will be several number of states which will be compatible with ER and ER prime. So, we are denoting that state, number of state is omega. Omega prime is a number. And you see, we can say this PR, the probability that the system would be in a state with energy, let's say ER, is given by PR. Okay, PR means the probability that the system would be in a state with energy ER, and it is found out to be proportional to this omega prime ER prime. This is the derivation of canonical ensemble, which we are not doing completely. We are just interested in the last result, and you have to remember that you don't need to be worried about this derivation things. You just need to understand that we have a system and a reservoir which are transferring heat among themselves or exchanging energy between them. So this omega prime is proportional to, so PR is proportional to omega prime, which is a function of E0 minus ER. And ultimately you will get a formula which you need to remember, that PR will come out to be e to the power minus beta ER divided by sum of e to the power minus beta ER, sum is on R. So this is the formula which you need to remember. The term in the denominator is known as the partition function of the system. Let's say Zn, or also people write Z beta. Qn also it is written. So this is a partition function which is sum of e to the power minus beta. This is known as the partition function. So n denotes the number of particles. If there are n number of particles, this partition function for n particles is Zn. For one particle it will be Z1. Okay. So what does this partition function do? It indicates how the particles are partitioned. The name speaks for itself. Partitioned among the various energy states of the system. So you need to remember these two formula. One is this probability for the system to be in the state with energy ER, and the partition function expression. Now if there may be degeneracy to a particular energy state, okay na? So if the levels have multiplicity or degeneracy or a statistical weight, then the formula will be changed a little bit. If the level have multiplicity or degeneracy or statistical weight, let's say GR, then the probability for the system to be in a state with energy, let's say E, instead of ER we can also write EI. So let's say ER is probability of the state being with energy. EI is equals to GI exponential, okay, ER if we are writing, so let's write that way, ER GR exponential minus beta ER divided by sum over R GR exponential minus beta ER. Okay, we did not define beta. Beta is equals to 1 upon KT. K is the Boltzmann constant, T is the absolute temperature. Now let's define the partition function. Okay, so we'll get two expressions. One expression we'll get for non-degenerate energy levels and for degenerate energy levels. For non-degenerate, as you have already told you, it is Zn is equals to sum over R exponential minus beta R ER. For degenerate, it will become sum over R GR exponential minus beta ER. I think R, okay, we can use I instead of R. R is not much used, so we can just change it. If you want, you can change. Like here for reservoir, to denote reservoir, we have used R, but for the upcoming derivations or nomenclature, we can use I. If you want, you can go with R, there is no issue, but you can change R to I. That will be more, that is more commonly used. So it will become GI, it will become EI, it will become EI, GI, EI, EI, EI. This will become EI, EI, GI, I. Anything is left? Is it clear or not? So here, as you can see, we have used the summation sign. It means it is applicable for discrete energy level, means quantum systems. If you have classical system, so in classical system the energy values are continuous, right? So we need a formula for that also. If the energy becomes a continuous variable, then we will write. So, you see here what we are saying, that the probability for a state with being an energy EI. So, we know exactly a discrete value of the energy, but for continuous, if the energy value is continuous, here we have to define, instead of a level of energy, you have to define a range of energy. A continuous range of energy, let us say between E and E plus dE. So, this spread is, let us say, dE. So, in that case we will write the probability for the state with energy between E and E plus dE, dE. So, for the, this is the you can say the more generalized case. If it is non-degenerate, then Gi becomes 1 for each state. Okay. So, it is Ge exponential minus beta E dE divided by integration. Instead of summation, we have to use integration Ge exponential minus beta E dE. The limit will be 0 to infinity. These are the fundamental thing. Okay. After that, we will go for some problem. When you consider thermodynamic system, it is mostly gas, consist of gas, right? It will consist of gas molecules. In the denominator of P of EI, the summation term will contain I. Yes. It is not mandatory to show every time that it is a summation on I. If you write summation I, even if you don't mention this I, it doesn't matter. Okay, so if I talk about the partition function of a single gas molecules, let us say the partition function of a single gas molecule is Z1, let us say. Then the partition function of n such non-interacting gas molecule is look, this summation sign will be used for quantum mechanical system, for example, one dimensional quantum harmonic oscillator. Okay, and this continuous sign summation, when we replace it with integration, it means it is applicable for continuous variable of energy, means energy value can be can take any value continuously. So, for example, classical ideal gas, if you treat classical ideal gas, then you will use this formula summation. When you are considering quantum harmonic oscillator, you will use this one. Understood, Murli? Now, the non-interacting gas molecules, they may be distinguishable and there may be indistinguishable. If you consider for distinguishable, so for one particle the partition function is Z1, for n particle the partition function will be Zn. This will be for distinguishable particle, it will be Z1 to the power n. Now, if you consider indistinguishable particle, which we cannot differentiate by looking at it, they are all looking identical. It is impossible to differentiate. For example, electrons, fermions, those are indistinguishable particle. So, for them the particle function formula for n particles will be z1 to the power n, as usual will be there, but there will be n factorial in the denominator. So, you must keep this in mind. So, when as you keep on doing problem, it will be clearer to you. Why not use the whole integration? Because it is energy, na? Energy of, let us say, gas molecule, it will not have negative energy. So, we are taking it positive 0 to infinity. It is like when the gas molecule is at rest, then we can take it the 0 energy. So, you imagine it like a classical ideal gas contained in an enclosure, and the number of gas molecules, let us say n. Okay, Murli. So, that is why we have taken 0 to infinity. Now, here also it will start from E0, then E1, E2, E3 and so on. Any more question, guys? Tell me. If not, then we will go for a problem. All okay? Is there any question from this theory part? Is the time to go for some problem? We'll do different kinds of problem so that everything becomes very clear to you. I is equals to 0, 1, 2. Yes, I will start from 0. The way we treat quantum mechanical system, is not I starts from 0, 1, 2. So, this takes discrete values. Yeah, let us go for this problem. The partition function for two Bose particles, each of which can occupy any of the energy levels 0 and E each. Can you do this problem? Partition function, you know the formula. Sum over I Gi e to the power minus beta Ei. Sorry, guys. So, we have a system which consists of two Bose particles, and there are available two energy levels, okay, 0 and E. Bose particles means they are identical particle, right? Fermions, sorry, bosons. Bosons are identical particle. So, let's say 0 E, and here we will write the total energy, and here you will be writing the degeneracy. So, how many probable combinations are there? 2 Bose particles are there. So, let us denote them. One particle is B, another particle is also B, because they are identical, indistinguishable. So, let us keep both the Bose particles at 0 level. So, there will be no particle in the E level. The total energy will become 0. 2 into 0 is 0. And what is the degeneracy here? It is 1. Let us say we keep one particle here, another particle in the energy level E. So, total energy will become, this is 0. So, this is 1 into E is E, degeneracy is 1, non-degenerates. And let us say we do not keep any particle here, and we keep both the particles to energy level E. So, total energy will become 2 times of E. Here the degeneracy is 1. Okay. So, what is the partition function for this system? Zn. Look, the partition function is a function of volume temperature. Zn is a function of Vt. This is equals to sum over I Gi e to the power minus beta Ei. So, you can see it is, you can start from 1 also. Okay. If you take it, let us say you are naming it, let us say E1, then you are naming it, it is up to you whether you will start with 0 or 1. It is just the naming, E0 or E1, whatever you start with, that will denote the ground energy, the ground level energy. So, either you can go for, let us say, in this way. So, it is better if you take, when you are considering this kind of particles, obviously it is like particle in a box type. So, you should start with 1. Okay. If you get a feeling like it is considering the harmonic oscillator, then you can start with 0. So, there is no such issue. 3 values of energy you have got, 0, E, 2, and they are not repeated. So, all of them are non-degenerate. So, e to the power beta E0 is 1, beta into E1 is 0. So, 1 plus e to the power minus beta E plus e to the power minus 2 beta E. So, it is matching with 1 plus e to the power minus E upon 80 plus e to the power minus twice E upon 80 is matching with option 2. Yes, option 2. Look, partition function of a classical ideal gas. So, classical ideal gas consists of n number of gas particles, and this is a classical system. So, we have to use the continuous formula. So, here the energy is written in terms of this energy, or Hamiltonian energy, what you can say. For classical ideal gas, there is no potential energy. If you consider, let us say, an enclosure, this we get from kinetic theory of gases. So, this is system of classical ideal gas. It consists of gas molecules, several gas molecules, let us say n number of gas molecules are there. So, they are continuously moving randomly, and they do not have any interaction, they are non-interacting. Okay. So, they do not attract or repel each other, they will exert force only when they are making a collision, and the collision time is very less. Okay. So these are there in the kinetic theory of gases. You can give a read to it. So the only source of energy these gas molecules have is the kinetic energy. And that is why in the Hamiltonian we get, let's say, if you take the ith particle, then its momentum is pi. So pi square divided by 2m. You know, the mass of all the gas molecules are same in a in this enclosure. So pi square by 2m, this is the kinetic energy of ith particle. So if there are n number of particles, the total energy will become I will run from 1 to capital N. If we consider there are n number of gas molecules there in the system. Okay. So therefore, the partition function Zn of Vt will be having value. You know, we have told you e to the power minus beta Ge exponential minus beta E dE. Okay. The actual formula, when you actually calculate it, it is a little bit different. Okay, before I derive it, we need to know another thing. We have to consider the phase volume. Okay, here we have written in terms of energy, but an interval of energy corresponds to a definite number of phase volume. So that correlation you need to maintain. Okay, we'll talk about that. For the time being, you just know the formula. Okay, integration e to the power minus beta E. So beta times this h, and I'm just writing the main formula d omega. It's a phase volume 1 by n factorial h to the power n. So you just know this thing, that an interval of energy corresponds to this many number of states in the phase space. So that is why the formula is changed little bit. Okay, this is the actual formula, but we have to consider it in phase space, and the formula is changed accordingly. This is in 3 dimension. If you consider the other dimension, for 1 dimension it will become 1 by h. You see, 1 by h. For 2 dimension it will be h square, and for 3 dimension it will be h cube, and there are n number of particles, it will become h to the power 3. Okay, and n factorial will be divided because these are indistinguishable particles. Is it clear now? You see, this is a 3-dimensional case. In 1-dimensional case, what will you write? You see, this is equals to 1 by n factorial h to the power 3n integration e to the power minus beta into h equals to I equals to 1 to n, okay, v square by 2m. d omega is the phase volume. So it is written as the product of I is equals to 1 to n d3qi into d3 ei. So in phase space, you know, p versus q, momentum versus coordinate, is represented. That is why the phase volume is the product of d3 qi and d3 pi. Can you digest this? So in 1 dimension, how this form will change? Look, if you consider 1 dimension, so h cube will be replaced by h, and d3q, d3p will be replaced by dq into dp. Okay, we'll do, don't worry. will do this derivations. This is equals to, now you see, if you closely look at d3q I is equals to 1 to n, what does it represent? Q is the position coordinate, you can say. So d3q I equals to 1 to n, it represents the volume, total volume of the container. Okay, so here product I equals to 1 to n, so this will become v to the power n, v to the power n, and this n factorial will remain as it is, h to the power 3n will remain as it is, and you see this d3qi and d3pi, they are in product. So this product, pi denotes product, I is equals to 1 to n integration e to the power minus beta pi square upon 2m d3 pi. Okay. So once you correlate this pi square by 2m with d3 pi, this summation sign is observed in the integration. Now what is d3 pi? This is the volume element in the phase space. So what is the volume element? d3 pi, you can write the way we write is 4 pi p square dp, right? So is it not coming in this form? This integration, if you look at it, is it not coming in this form? Let's say if you consider 0 to infinity e to the power pi square, and this is a constant, so it is like minus a p square, and this d3 pi means 4 pi p square dp. So it is 4 pi, you ignore for the time being, p square dp. Is it not coming in this form? So can you evaluate this value? This is equals to how much? Let a p square equals to z. So p square is equals to z upon a. That means p is equals to square root of z upon a. So what is dp? dp is equals to 1 upon 2 root a z to the power minus half dz. You can just put the values here, 0 to infinity e to the power ap square is equals to z, so e to the power minus z into p square means z upon a, dp is equals to this. Let's just put this value 1 upon 2 root a z to the power minus half dz. A and a to the power half, a to the power 3 by 2. So this is equals to 1 upon this 2a to the power 3 by 2 integration 0 to infinity e to the power minus z, z to the power 1 minus half is half. So half we are writing 3 by 2 minus 1. What is this kind? What is this formula? Look, I hope you have understood this. Z to the power 1 into z to the power minus half. So 1 minus half is half. So half we are writing 3 by 2 minus 1. Why you have written it in this way? Because we know that gamma n, gamma integral is equals to 0 to infinity to the power minus x to the power n minus 1 dx. To apply this formula, we have written it in this way. So, what is this integration value? This is nothing but 1 upon 2a to the power 3 by 2. This is gamma of 3 by 2. And you also know a formula, gamma n plus 1 is equals to n gamma n. Okay. So, this is equals to 1 upon 2a to the power 3 by 2 half gamma half 3 by 2, you can write half plus 1, right? So, half gamma half is equals to root pi. Root pi is divided by 4a to the power 3 by 2. So, if you just put this value back into this integration, what we will get? Zn of Vt, this is equals to, you see, v to the power n divided by n factorial h to the power Tn will remain as it is, and the integration will produce 2 pi m a t to the power 3 by 2 whole to the power n. Whole to the power n is coming because of this product I is equals to 1 to n. Let me know if you have if you are understanding it or not. We have put the value of beta is equals to 1 upon kt. So, this is like minus pi square by twice m kt. So, a is equals to 1 by twice m kt. Is it understood, guys? Tell me. Would you understand, or should I explain it more? Look, d3 pi, so 4 pi will remain as it is, e to the power minus pi square by twice m kt p square dp. Actually, this is the formula. So, 4 pi, so 4 get cancelled, so pi to the power 3 by 2, okay, and 1 by twice m kt, that is a, and here it is 1 by a to the power 3 by 2, so twice m kt to the power 3 by 2, simple. Here in this expression, just write d3 pi is equals to 4 pi p square dp. So, the integration becomes e to the power minus pi square by twice m kt, p square, let us say, instead of writing pi square, okay. So, you can okay, this pi you can consider to be p. So, a is equals to 1 upon twice m kt, right. So, our result is root over pi by 4a to the power 3 by 2. So, pi to the power half divided by 4 into a to the power 3 by 2. So, a is 1 by twice m kt. So, twice m kt will come in the numerator to the power 3 by 2, and this 4 pi will be there. So, 4 pi. So, 4 get cancelled, pi to the power 3 by 2. So, we are inserting into this expression of and this product pi was there, pi equals to 1 to n. So that is why there is to the power n. Now is it clear? Now you can do one thing, 1 by n factorial. If I write it v by h cube 2 pi m k t to the power 3 by 2 whole to the power n. So we can write z1 to the power n divided by n factorial. Z1 is equals to v by h cube 2 pi m k t to the power 3 by 2. So this is the partition function for a single particle, single molecule. Z1 is the partition function of a single molecule. And Zn is the partition function for the n number of molecules. Which formula we should remember? Actually, this derivation you need to do. Here nothing to remember. You know partition Hamiltonian of an ideal gas is this. So this is the actual formula, more generalized formula. Zn Vt is equals to 1 by n factorial h to the power 3 n e to the minus beta h d omega. D omega is the phase volume. So you must remember the first formula. Then the other things are following automatically. So practice this derivation quite a few times. Then you will understand, otherwise you will forget. So whatever system you will be given, whether it is if it is given to be classical, you will use this first formula. Zn Vt is equals to 1 by n factorial h to the power 3 n e to the power minus beta h d omega. Is it clear or not? Whatever we have derived here, is everything all clear? So this is the case of classical ideal gas, right? So let us try to understand what it will be if you consider one dimensional quantum harmonic oscillator, classical harmonic oscillator. If we talk, then what kind of change you will see in this formula? That will help you to correlate between the two. So let's go for classical harmonic oscillator. When the oscillators are treated classically, the Hamiltonian is given by h of qp. So for classical harmonic oscillator, we know the kinetic energy p square by 2m, not about the potential energy, half m b square, so half kx square actually, sorry. So half m omega square q square. So if I write it for n number of such systems, so we will write it function of qi pi, so pi square half m omega square qi square, where I may be 1, 2, 3 up to n. Let's say there are n number of classical harmonic oscillators. So if I only go with one oscillator, we will get the partition function for one oscillator. Then we know the formula. We know the formula. Okay, this formula we know for distinguishable case. If it is distinguishable, then if you want to calculate partition function for one particle, it will be for n particle it will be to the power n, and for indistinguishable to the power n divided by n factorial. So this is what we have. So let's calculate for the single particle. For the single particle partition function, let's say we are denoting it by Z1 Vt. We are not denoting it with Zn Vt, we are denoting it by Z1 Vt. Try to understand it very carefully. You see, look at the formula 1 by n factorial. Now we are calculating for one particle, so 1 by 1 factorial. So 1 h to the power 3n. This is in 3 dimension for n particle. For 1 dimension, as I told you, h will be there. For 2 dimension, h square will be there. For 3 dimension, h cube. And n is the number of particles. So what should I write here? 1 upon h, because this is one dimensional harmonic oscillator, right? N is not given because we are calculating for one particle. Integration exponential minus beta h d omega. Here, what is this d omega? D omega is the phase volume. So for one dimension, it will be what? Look, why we write d3q, d3p? This is in 3 dimension, the phase volume. Now, when you consider 2 dimension, it is d2q, d2p. For one dimension, it will be dq, dp. Okay. So this is equals to 1 upon h e to the power minus beta into h. H equals to this. For one particle, we are writing by 2m plus half m omega square q square, d omega is dq dp. Now there are two variables here, q and p. We have to write it through integration. So if you consider what kind of structure you will see, I am just drawing a rough picture. It is like this. For a particular value of energy, you get an ellipse in the phase space. P and Q, it gives you an ellipse. This is valid for a particular energy. Now there is, if you are considering classical harmonic oscillator, the energy can vary between 0 to infinity, any value. And as a result, this ellipse will keep on growing. Okay, more the area of the ellipse, it means more the energy you can consider. So here Q and P, they can vary from minus infinity plus infinity. No issue? So let's just separate the quantities for Q and P. Minus infinity to plus infinity e to the power, you see, minus half m omega square beta q square, okay, dq, and e to the power minus beta p square by 2m dp. Can I write it? They are in product. We have just separated the variables related to q and p. Now you know a formula, you know this formula, right? Minus infinity to plus infinity e to the power minus square dx. This is root over pi by a. Do you know this formula? We are going to utilize that formula. Root over pi by a. A is this beta m omega square, and this 2 will go out. Here the product pi by a, beta p square actually a is equals to beta by 2m, beta by 2m. So what are you getting? One by h into 2 pi, mm get cancelled, divided by beta square omega square, so square root, so beta omega, h by 2 pi is h cut, so it is nothing but, look, beta is equals to 1 upon kt, okay, and h by 2 pi is h cut, so h cut omega by kt, so we can write h cut omega by kt inverse. So we can write therefore the partition function of a system having n such classical harmonic oscillators is Zn. Zn will be Z1 to the power n h cut omega by kt to the power minus. Look, in the question, classical harmonic one dimensional, actually this we should write it as, this is considering one dimension. Now, if in your question, if they mention that it is distinguishable, then we can write it, this formula. If they mention that the harmonic oscillators are distinguishable, then you will use this formula. and otherwise you can use for indistinguishable 1 by n factorial will be multiplied. बताइए दोस्तों, कोई प्रॉब्लम या समस्या इशू है क्या? Now I think you will be able to tackle any of the given system. If you are given the dimension, the Hamiltonian, you can easily find out the partition function. Are you confident, guys, now? If you are not feeling confident, don't worry, we'll do a lot of problems and after that you will automatically be confident. You can ask me till now whatever we have discussed, is there any confusion, any single confusion? If you have, you can ask. I will definitely try to clarify all your doubts. No confusion? Can you go to the next problem? Let's take this same oscillator, but now instead of classical we are giving you quantum harmonic oscillator. How will you deal it? So this is the problem. I have just kept them one before another, just so that you can distinguish. An ensemble of quantum harmonic oscillator is kept at a finite temperature T. The partition function of a single oscillator with energy n plus half h cut omega is given by. From the energy value, we are sure that it is talking about one dimensional quantum harmonic oscillator. We have to find out the partition function for single oscillator, not the n number of oscillator. Single oscillator you have to find out. Can you do this? This single oscillator can take any of the energy values starting from half h cut omega to various values of energy n. You can put n equals to 0, 1, 2, 3 and up to infinity and put. Will you give it a try? Harry, Murli, tell me. So here you don't have to use the continuous formula. Here it is quantum, so we can use the summation formula. Hurry up, guys. Simple problem. It should not take much more time. Tell me the option quickly. Which option you are getting it correct? Option 2. Are you sure? Plus or minus? Let's do it. So let's write Zn one particle. So Z1 of Vt. You know the formula. Look, one dimensional quantum harmonic oscillator, they are non-degenerate, right? There is no degeneracy. So if they are non-degenerate, we'll use the formula of non-degenerate. So integration I, Gi is not there, e to the power minus beta Ei. Okay, so Ei is equals to n plus half h cut omega. So sum over e to the power minus beta times n plus half h cut omega. So obviously this summation will now change be n. So we will be putting different values of n. N starts from 0, 1, 2, 3 and so on. So you see, if you put n equals to 0, it becomes e to the power minus beta h cut omega by 2. If you put n equals to 1, e to the power minus 3 by 2 beta h cut omega. If you put n equals to 2, 5 by 2 beta h cut omega, then 7 by 2 and so on. You will get it. Now, we can take e to the power minus beta h cut omega by 2 common. What you are left with 1 plus e to the power minus beta h cut omega. Every time one unit is changing, right? Beta h cut omega is changing. E to the power minus 2 beta h cut omega plus so on. And you know a formula that if you have, let's say, 1, if you have, let's say, 1 plus x square plus x cube and so on. What is this value? This is 1 upon 1 minus x, right? So let's use this formula here. E to the power minus beta h cut omega upon 2 divided by, it is like 1 plus x square. X is e to the power minus beta h cut omega, so it is 1 minus e to the power minus beta h cut omega. Which option is it matching with? I think option 1 is matching. Okay, got it. Harry, Murli, Joel, Ajay. So you see, when we are considering the harmonic oscillator, classically we are getting this kt by h cut omega or h cut omega by kt inverse. But if we are treating it quantum mechanically, we are getting it e to the power minus beta h cut omega by 2 divided by 1 minus e to the power minus beta h cut omega. So you know the difference. Ensemble, we have not given you the exact concept of ensemble. Ensemble, you can imagine it in this way. Same system, its snapshot is taken at different times, okay, and put it together. It is like the ensemble. So these are like mental copies of a system. So let's say you are observing a system, you are taking a snapshot. At that particular time, the system will have some structure, some thermodynamic specifications. Now as time moves on, you take snapshot of the same system, and you know the quantities are changing. So if you put all these snapshots at one place, so that is the ensemble. So in one particular snapshot, the thermodynamic description will be something, and at some other snapshot, the thermodynamic description will be different. So ensemble average of a physical quantity. So a quantity, how it is varying over different ensemble, different member of the ensemble. So average of the instantaneous values of f over each member of an ensemble. So it is like you have taken the snapshot of the system at different time interval, and basically they are representing the same system, but it is like you have taken the snapshots at different time. So you can produce it like this. The different thermodynamic quantities values will be, this is system 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is ensemble. Average of the instantaneous value of f over each member of an ensemble. These all box represents member of the ensemble. We'll talk about this in more detail in some other videos. For the time being, you understand this. The any quantity. F may be anything, it may be distance, it may be velocity, or it may be something else. So that quantity you have to measure on all the ensemble, on all the member of the ensemble. The average value of the instantaneous values of F over each member of an ensemble is called the ensemble average, and mathematically we represent it by F. F may be any quantity, it may be temperature also. F function of Q and P, rho function of Q and P, D3 and Q, D3 and P divided by rho QP, D3 and Q, D3 and. So you can remember this formula, you don't need to remember, you will remember the slightly modified formula. This can be written as f of u e to the power minus beta h. So this density is proportional to e to the power minus beta h, and this d3 and q, d3 and p, you know, that is represents h volume e to the power minus beta h, where this d omega, d3 and q, d3 and p denotes a volume element in the phase space. And you know why we could write this? Because in canonical ensemble, this density of states, rho of QP, this represents density of state, is proportional to e to the power minus beta h of Let me know when it is done. I am giving you a problem which will make it more clear. Give it a try. You see, this problem can be done in other ways also, but using the concept of ensemble average, this problem can be done easily. A particle is confined to the region x greater than 0 by a potential which increases linearly as u of x equals to u naught x. The mean position of the particle at temperature T is. So here f is this mean position. You have to calculate x average. Do it. Look, a particle is confined to the region x greater than 0 by a potential which increases linearly as u of x equals to u naught x. So, from this x values we are sure that it is talking about one dimensional case, right. So, what will be the Hamiltonian for this particle? You know, function of q and p. Q is x here, p will be px. So, the kinetic energy will be px square upon 2m. What is the potential energy? Will be u naught x. So, ensemble average mean position. What is the formula? Integration f of qp. So, it is f is x e to the power minus beta h d omega. In one dimension it will be only dx dpx divided by integration of e to the power minus beta h d omega, e to the power minus beta h d omega h dx dpx. If it had two dimensions, let's say it would have been dx dpx into dy dpy. 3 dimension dz dpz will also be multiplied. Okay, so dx dy dz, that is d3q, dpx dpy dpz, that is d3e. I hope you are getting everything now. So, what you can write? Integration x e to the power. There are two integration variables, so there will be two integrations. Okay, x e to the power minus, let's write it for the time being, beta is equals to 1 upon kt times h is this, put the value, multiplied by dx dpx. No issue till now. This is equals to, you can see the condition x greater equals to 0. Okay, so we can write it in this way. Let's say integration, let's consider the p part first. So e to the power minus px square divided by twice m kt into dpx. Another integration x times e to the power minus u naught x by kt dx. Here also we are just separating e to the power minus x square by twice m kt dpx e to the power minus u naught x by kt. So as you can see, this integration and this integration are same, are cancelled. So you are left with x e to the power minus u0 x by kt dx divided by e to the power minus u0 x by kt dx. X is greater than equals to 0, it is given in the question. So from here it can vary from 0 to infinity, also 0 to infinity. Now you know the formula. Zero to infinity e to the power minus alpha x x to the power n dx is equals to n factorial by alpha to the power n plus 1. Do you know this formula? In mathematical methods, we have given you all of this formula. Or if you do not want to use this formula, you can do another thing. You can use gamma integration. Okay. So let u naught x by kt is equals to t. It means dx is equals to how much? kt by u naught. So you are left with 0 to infinity x is equals to how much? kt by u naught into t. E to the power minus x dx is kt by u naught into dt. kt by u naught once again, so square divided by 0 to infinity e to the power minus t dx is kt by u naught dt. So kt by u naught, 1 kt by u naught is cancelling from both numerator and denominator. E to the power, you know the formula of gamma function, e to the power minus x to the power n minus 1 dx is equals to gamma n. So here gamma 2, the numerator is e to the power minus t to the power 2 minus 1. So this is gamma 2, and here it is 1 minus 1 is 0, so gamma 1. What is the value of gamma 2? Gamma n plus 1 is equals to n gamma n. So gamma 2 is equals to 1 plus 1, so 1 gamma 1. 1 gamma 1 is 1, so 1. So this is equals to kt by, matching with option A. Understood how we are getting things? Let me know once it is done. Is it clear, guys? Tell me quickly. Look, this one here we have used the continuous case. So if we have discrete system, what changes we can have here? Tell me. So it will be, if we consider Look, for continuous case there is no question of degeneracy, but for discrete case there may be degeneracy, there may not be degeneracy. If you are calculating for f, so you have to consider the degeneracy of the quantity fi e to the power minus beta ei divided by gi e to the power minus beta ei. Can you write it? This is the ensemble average. Sum over I gi fi to the power minus beta ei divided by sum over I gi e to the power minus beta ei. So straightforward. Let us try to understand it with a problem. Okay, this problem, a two-level system has energies 0 and E, no issue, 0 and E, obviously they are non-degenerate, the level with 0 energy non-degenerate. Acha, it can be having multiple degeneracies, so this is having 0 energy, this is having energy E, this is non-degenerate, only one energy value. Level with energy is triply degenerate. Triply degenerate means the degeneracy is 3, 1, 2 and 3. Okay, so all of these levels are having the same energy. The mean energy of a classical particle in this system at temperature T is. Can you do it? Do it quickly. I think you can do. Hurry up. Tell me the answer quickly. Mean energy. Do you know the formula? This is discrete. You can easily see these are considering discrete energy levels. So gi fi is ei here, e to the power minus beta ei, so ei by kt divided by sum over I gi e to the power minus beta ei. Option D, Joel, very good. So here only I will be from 0 and 1, right? For I equals to 0, it is considering 0 level. So this is non-degenerate. G1 is equals to 1. Energy value is 0 e to the power minus 0 by kt plus energy level is triply degenerate, energy is e to the power minus e by kt. Here this is 1 into e to the power minus 0 by kt plus 3 e to the power minus e by kt. So this is 1 plus 3 e to the power minus e by kt divided by 1 plus 3 e to the power minus e by kt. It is matching with option D. ऑप्शन डी यस। गुड मॉर्निंग नेहा, कैसे हो? बहुत दिन बाद आए हैं नेहा। चलिए लेट्स डू दिस प्रॉब्लम। अजय, हैरी, मुरली, यू गाइस आर गेटिंग डी? First term is 0 in the numerator. Yes, yes. Let's do another problem. Yes, this one. Consider n non-interacting distinguishable particles in a two-level system at temperature T. The energies of the levels are 0 and E, where E greater than 0. In the high temperature limit, kT by E much greater than epsilon. What is the population of particles in the energy level with energy E? Population means what is the number of particles. Actually, we have two energy levels. Okay, one is having an energy 0, another one is having energy epsilon, and epsilon is given to be greater than 0. Look, if we multiply the total number of particles with probability, that gives you the number of particles into that particular level. Let's say the probability of getting this energy level is 0.35. Okay, so how many particles will be there? It will be n into 0.35. Let's say 100 particles are there. 100 particles are distributed in two energy levels. If I say the probability for this energy level is 0.60, the probability for this energy level will be 0.40. How many particles will be there? Out of 60 particles, 100 particles, 60 particles will be here, 40 particles will be here. If I say the probability here is 0.3, here the probability will be 0.7. So how many particles will be there? Probability into total number of particles. So 30 particles will be here, 70 particles will be the epsilon level, you can say. Clear? So if you want to calculate the population of the particle in the energy level E, if you somehow calculate the probability for this energy E, then if you multiply with the total number of particles, that will give you the population, isn't it? भी ठीक है. Do this problem. So initially we have given you the formula of P of epsilon. You can use that formula, है ना? Kt is much greater than epsilon. It means Kt by epsilon is much greater than 1, or epsilon by Kt is much less than 1. So what do we know? We know that the probability of system to be in a state with energy EI each obviously this is the discrete case, so we are going to use this formula Gi e to the power minus beta ei divided by sum over Gi e to the power minus beta ei. Here there is no summation in the numerator. If you check the formula, it can check. So, what will be the probability for the system to be in the state with energy E? In place of EI, you will just put E. So, GI, it is non-degenerate. So, it is GI is 1. So, e to the power minus beta EI is epsilon divided by, here sum is there, means we have to do the summation on both the states, on this state and on this state. Here GI for the 0 energy, GI is 1 non-degenerate, e to the power minus beta into 0. This is the first term. The second term will be for this energy level, that is also non-degenerate, e to the power minus beta, energy is epsilon. Okay, so this is e to the power minus beta epsilon divided by 1 into this is 1 plus e to the power minus beta E. So, we have got the probability. Now, if there are n total n number of particles, so what is the population? Therefore, the population of the particles in the level with energy epsilon is probability of being in the state with energy E multiplied by the total number of particles. So, this will be n times e to the power minus beta E divided by 1 plus e to the power minus beta E. Now, if I look at the option, is it matching with any of the option? No, it is not matching. So, let us simplify it. So, we can just divide both numerator and denominator by e to the power minus beta E. So, numerator will become n, here e to the power 1 by e to the power minus beta E, e to the power plus beta E plus 1. Can you write option C, Neha, you are getting? Option C or option A? Look, beta E firstly let us consider beta E. Beta E is equals to E by kT. E by kT, it is given to be much less than 1, much less than 1. So, you know, if x is very small, then e to the power x, we can approximately, you can write it, is 1 plus x by 1 factorial plus x square by 2 factorial plus so on. If x is very small, we can write it approximately 1 if x are negligible. So, we can write e to the power minus beta E to be approximately 1 n by 2. Is it clear or not? Tell me quickly so that we can go to the next problem. Is it done, guys? Tell me quickly. Let's go to the next problem if it is done, or if you have any question you can ask. A particle of mass m is confined into two-dimensional square box at temperature T. If the ground state energy is 2E0 and Z is the partition function, then the probability that energy is less than 9E0 each. It's a very interesting question. So it's a 2D box. So you know, particle in a 2D box, it is a mixture question, mixing of quantum mechanics and statistical physics. So for 2D box, you know the energy level E nx ny is equals to n square pi square h cut square by twice m a square. Nx square, if it had, it is for one dimension. For two dimension, there is another term ny square. Okay. Now what will be the ground state? Depending on the various values of nx and ny, we get ground state or excited state or not. So here for particle in a box problem, you have seen that nx starts from 1, ny also start from 1. 0 value is only for the harmonic oscillator. Okay. So if I talk about the ground state, if I choose n equals to 1, nx equals to 1, ny equals to 1, then that will give you the ground state. So what is the degeneracy? Degeneracy is 1, only one combination. Okay. So what is the energy? Ground state energy is 2E0. E11 nx ny, nx equals to 1, ny equals to 1. So this is equals to pi square h cut square by twice m a square 1 square plus 1 square, 2 times pi square h cut square by twice m a square. This is given to you as 2E0. So we can say that E0 is equals to pi square h cut square by twice m a square. Can you write it? So if you put higher values of nx and y, you get higher energies. So if I talk about the first excited state, this is the ground state energy, right? This is the ground state energy. Now the next energy will be first excited state energy. First excited state energy. First excited state, how will you get? So you previously choose n equals to 1, nx equals to 1, ny equals to 1. Now if you choose nx equals to 1, ny is equals to 2, or if you choose nx equals to 2, ny equals to 1, in both cases you get the same energy value. Okay, either you choose nx equals to 1, ny equals to 2, or you choose nx equals to 2, ny equals to 1. In both the cases you get it two square plus 1 square, or 1 square plus 2 square, same thing. You are getting a 5 times pi square h cut square by twice m a square. So this is 5 times E0. Here what is the degeneracy? It is 2, right? Because by choosing nx equals to 1, ny equals to 2, you are getting same value of energy, and if you choose nx equals to 2, ny equals to 1, then also you are getting the same value of energy. So these possible combinations are corresponding to a single energy value. That is why G is equals to 2. The first excited state energy. Now if I talk about the second excited state energy, second excited state energy, what it will be? Look, if you choose Nx is equals to 2, Ny is equals to 2, then what are you getting? 2 square plus 2 square, so 8, 4 plus 4, 8. If you, why not 3, 1? Because if you choose 3, so 3 square plus 1 square will be 10. But if you choose 2, 2, 2 square plus 2 square, so 8. So 8 is less than 10. So that is why then it is like the energy value is continuously increasing. Right? In the first you are getting 2 E naught, in the second you are getting 5 E naught, in the third you will get 8 E naught, right? The E 2 pi square h cut square by twice m a square, 2 square plus 2 square. So this is 8 pi square h cut square by twice m a square, 8 E naught. Here the degeneracy is okay. So then the probability that the energy is less than 9 E naught. If you consider the next third excited energy level, that will be 3 1 or 1 3. So that will be 9 E naught, but you have to consider the energy level which is less than 9 E naught. Less than 9 E naught, which are the energies which are less than 9 E naught? We have got 2 E naught, we have got 5 E naught, and we have got 8 E naught. So all these three energy levels are less than 9 E naught. So what is the probability that these energies will be less than 9 E naught? So this is what we have to find out. So therefore the probability for the state with energy which is less than 9 E naught, it is, you know the formula, 1 upon z into gi e to the power minus beta ei. Okay, 1 upon z multiplied by e to the power minus 2 beta E naught, degeneracy is 1, next is degeneracy is 2, e to the power minus 5 beta E naught. Acha, so it is like probability for the state with energy 2 E naught plus probability for the state with energy 5 E naught plus the probability for the state with energy 8 E naught. So for all of them we'll get e to the power gi e to the power minus beta by z. So 1 by z we are taking common, e to the power minus 2 beta E naught plus e to the power minus 5 beta E naught, and here gi is 2 plus here it is 1. Look, it is clear or not? It is matching with option D. You have to revise it, okay, and then you will understand. These are very simple questions, but if you are learning it for the first time, you may find it a little difficult. So I will recommend you to revise it 2-3 times, and after that if you have any question we can discuss it on the next day. I'm giving you one homework that you can try at home, and we'll start from here. Consider a gas of identical but distinguishable quantum particle of mass m is subjected to a 3-dimensional potential. This is a 3D harmonic oscillator potential. You can see the gas is in thermal equilibrium. The temperature of the system such that the number of particles in the first excited state is equal to that in the second excited state. So similar concept you can use to do this problem. So take this as homework. We will start from here. We will do the solution of this homework in the class itself. So we will start from here. So we are stopping here today, guys. Thank you very much for joining the session. I hope you enjoy the session and you're finding it useful. If you're new to this channel, please subscribe the channel and don't forget to press the bell icon. And if you want to get enrolled to this top 100 most important topics course, you can enroll. Links are given in the description. Thank you, guys. Thank you very much. Bye bye. Take care.